I'm going to say that we did and move on, but today we're talking about Newton's second law. I was tutoring last night, and something came up that I think bears at least a little bit of discussion. Newton's second law says the sum of all forces equals ma. And although we've talked about this already a little bit, last night somebody brought something that I was a little surprised by. M here stands for inertial mass. This term stands for net force. And the word net here means to sum up all the forces. There should be a bar on top of these to indicate that the unbalanced force has to be in the direction of the acceleration. So those are all details that seem subtle, but they become more important as we start getting down to the particulars of how we do this. A represents something you already know. This is a change in motion or change in velocity. So something has to be changing for there to be an acceleration. Newton's second law refers to systems in which there's an unbalanced net force, meaning net force isn't zero, it is unbalanced. So when you add up all those forces, they are equal to ma. It doesn't have to be a single force that is causing this. It's the sum of the forces that cause this. And it's the direction is going to be based on the sum of those forces. But this came up last night, and I need to make sure we all know this. Mass is in kilograms, and acceleration is in meters per second squared. So that means that our unit for force, which is on the left side here, our unit for force is the kilogram meter per second squared, which is called a Newton. Somebody last night didn't know that at tutoring, so let's make sure we know that. This is the complex unit, but we call it a Newton. So all of our units are very likely to have names that are shorthand for the complex unit. But all of our units have a complex notation. We could write kilograms meters per second squared every time. It's just easier to write a capital N. You follow me? I hope so. We're going to call this example 0. And I'm doing this because I want you to be able to see that there's a slight modification you have to make to your force concept model in order to do these problems. And I want to kind of show you that right away, but it's not really an example. It's not what I will expect you to do. It's way beneath what my expectation is for what your capabilities will be. So I don't want you to become expectant that this is what you will be doing. But I want to show you how it's different now than it was before. So just imagine a straightforward wagon with some wheels on it, without any friction. And let's say it's not particularly heavy, so we'll say it has a mass of 5 kilograms being pulled with a force, say this way, of 20 newtons at an angle of 15 degrees. All right? And we're going to say no friction. Every one of our problems, we generally start with asking ourselves, is it a first law problem or a second law problem? I've been trying to say that from the beginning, but remember, a Newton's law problem is going to ask something of you, but the force concept model tells you only one of two things. It tells you an acceleration or it tells you a force. That's all it can tell you. So although in these problems, we have a procedure, the procedure is about analyzing the situation. It's not necessarily about answering the question. When we're done, you're going to be left with something that may or may not answer a question. I'm not asking a question right now. I'm just telling us to analyze this situation according to the force concept model. This is going to generate two relationships. So that's what I want to do. I want to do the process we know about that deals with finding what happens to these forces and resolves them into something that we may or may not be able to use to answer questions. The force concept model. So this is a Newton's second law problem. The forces are unbalanced. If there's no friction, when I pull on the cart to the right, it's going to accelerate. What that actually means, I don't know. We're going to find out. Now our set of steps really doesn't change very much. We're still going to draw in all the arrows like we have before. For example, I'm going to start with the downwards arrow. That indicates the weight of the object. It's a 5 kilogram object. This weight is 50 newtons. Whether you write W, mg, or 50, I don't care. But if you're going to write 50, make sure you put the units there. All right? So there's no confusion on the test. Any of these are fine. There's a force to the right and slightly upwards. It should be less than the 50 because it's 20. But I'm not sure you can only make it small, too small. You won't be able to work with it. So I'm making it big enough to see, but I'm making it clearly smaller than the 50. I'm going to label it, though, as just 20 newtons. That's all I know about it. I'm not going to put the angle in because I haven't decided what my coordinate system is yet. The angle will be based on what coordinate system I choose. There'll be a normal force, though, and I need to make that less than the weight as well. I am pulling upwards on the wagon a small amount. The normal force will not be equal to 50. These are all reasonable, common sense things. It's what I would expect a reasonable student to be able to do. Now, we reach the point where we have to decide something. We're going to decide the coordinate system to apply to this problem. You have two priorities. First priority is to align the coordinate system with the direction of the acceleration. We've never used that before because we haven't had any acceleration. We have an acceleration now. Do you know the direction of the acceleration? I'm hoping for common sense here. And I say this knowing that people in first period suggested some interesting things, but I am pretty sure that's got to be the direction of the acceleration, right? It's going to go along the ground. I'm not lifting so hard, I'm lifting it off the ground. So deciding the direction of the acceleration seems minor, but you need to assess your problem and decide what you believe is the appropriate direction for the acceleration. I think it's that way. And since the system is accelerating, I'm going to use a coordinate system that's aligned with the acceleration. Now, once I've chosen a coordinate system, I need to apply it the same way to all of the system. So I'm applying it to the x and the y. I'm making sure that they are perpendicular to each other. Now you'll recall the next step is to resolve your forces. Since I lined up the x direction with the horizontal, that does make this 15 degrees. And that does mean that I have this, which is going to be 20 cosine 15, and this one, which is 20 sine 15. Any questions about those choices? All right, look, some of you are really struggling and you can't do this. And the next part you have difficulty with as well. When we break up our forces into the components, I notice that there's 1, 2, 3 arrows that point up and down. Do you notice that? Remember, the components, I'm using the words, these are the components of the 20 Newton force. That's the only force I broke up into components. Once I broke those into components, this no longer matters, the 20 Newtons. I ignore it. The components take up the actual force. I notice only one force is to the right. Do you guys notice that too? So I have 3 forces that are up and down and 1 force to the right. Because we're going to break this up into the x direction and the y direction, you need to know what goes where. It's all weird stuff on those tests. Now, net force in the x direction, net force in the y direction. In your notes, here's where you need to make an amendment to your force concept model. So wherever your force concept model notes are, I would make a change right here. When you are applying Newton's laws and you have made the decision that it's a second law problem, ready? The reason you line up one of your coordinates with the acceleration is so that you can make one of these 0 and make only one of these MA. Again, the reason you line up one of your coordinates, one of your axes with the acceleration, is so that one of these can be made the acceleration and the other one can be made 0. You can choose any axes you want, but if you don't line it up with the acceleration, then you have to make one of these MA in the X direction and one of these MA in the Y direction. And you understand that that's going to make this a lot more challenging now, because you're going to have 2 accelerations that you'll have to resolve. Don't do this. This is well beyond your capabilities, and if it's not, it's a lot more work. So you do everything you can to line up one of your axes with the direction of the acceleration. Notice I'm very careful to say this, and I'm going to say it again. You line it up with the direction of the acceleration, not the direction of motion. You line it up with the direction of the acceleration. In big blinking letters in your notes, write down not the direction of motion. This one's stupid easy. That's why it's example 0. But we are going to have plenty of examples where the acceleration is not in the direction of motion. And you will put the coordinates in the direction of motion and be wrong. So you must line up the X or Y direction with the direction of the acceleration, not the direction of motion. All right. Try to make sure you have it in your notes correctly. But here we go. The rest of this problem is something you've already done. We add up all the forces in the X direction and add up all the forces in the Y direction. They're pretty easy here. Normal plus 20 sine 15 minus 50 equals 0. That's the Y direction. And on the X direction, I have 20 cosine 15 equals MA. The force concept model produces a relationship that may or may not answer your question. Well, you didn't have a question. You were just supposed to do the analysis. But I see some questions you could answer. You could tell me what the normal force is. That's something that the force concept model will do. It will tell me one of the forces. You could also tell me what the acceleration is. That's another thing the force concept model can do. It can tell you the acceleration. So I'll remind you that the whole point of the analysis is to present you with some relationships that you may or may not be able to use. Hopefully, you'll be able to use them to answer your question. All right, example 0. I gave you new information to put into your notes about what direction to make the positive X or Y direction and why. Does everybody understand? Your goal is still to make sure one of these is equal to 0. All right, so let's do a problem. It should not be hard for you to figure this out. Most of you were able to take the information from here and find successfully what you needed. For example, you figure out that this is 3.86 meters per second squared. This is the acceleration. Once you had that acceleration problem, this is example 1. And since we just did this problem, this one should be really easy for everybody, so I'll be able to walk around and see all of your success in about 2 minutes. Same everything. Same cart, same size of forces. You don't have to change very much. So I have my cart. I have my pulling force. It's still 20, still at an angle of 15 degrees. And my cart's 5 kilograms. Everything's the same. Okay. All right. Here's your question. I have a cart being acted on by a 20 Newton force at an angle of 15 degrees to the horizontal. The cart has a mass of 5 kilograms. How long until the cart is traveling 10 meters per second? This is example 1. And I want to tell you exactly what this example is about. This is a Newton's second law problem where your solution for Newton's second law is used in a kinematics equation. Meaning in this problem, you're asked about the kinematics of a system. You have to use Newton's laws to derive the kinematics. let's look at the kinematics problem for just a minute. The kinematics problem has standard kinematics things. Cart starts from rest. It's going to be traveling up to 10 meters per second. You're being asked how long it takes for that to happen. It's a kinematics problem. In order to solve a kinematics problem, you need 3 pieces of information. Obviously, you don't have it right now, but you do have quite a bit of information you could use to help you figure this out. Newton's laws are all about forces and accelerations. It is likely you could use this system to figure out the acceleration by using Newton's laws. Now, we just did this, so I'm going to walk around and look at people's papers, but I want you to do this as example 1. Find how many seconds it takes for the cart to be traveling 10 meters per second. All right, so I'm seeing quite a bit of correct work, which is good. You're able to come over here and say, okay, 3.86 meters per second squared. You found an appropriate kinematics relationship, V equals AT plus V naught. We worked it out to find that the time is like 2.6 seconds. All right. So as our example 1 goes, not particularly terrible. Nice introduction, pretty simple. All right. Example 2. Same level of difficulty, I think. Try and make it as straightforward as possible so that we ease into this, because they are going to get a little harder. I've got a box that's about to enter a rough patch here. It's traveling at 8 meters per second, and when it leaves the rough patch, it's traveling at 6 meters per second. And the rough patch is 3 meters long. Box has a mass of 5 kilograms like before. What is the coefficient of friction acting on the box? What is the coefficient of friction So we're going to start this problem the same way we started all the others. I have a lot of kinematics information here. I see all of that. But the problem is about friction. That's clearly about force. So I'm going to start as a force problem. And the place that I'm interested is while the cart is on this patch, where it's traveling this way with some velocity that's between 8 and 6. This all good? All right, free body diagram, right? Because force concept model can tell me about forces. I'm looking for the coefficient of friction that's about 2 forces. Friction is equal to mu times the normal force. So if I can find the frictional force and I can find the normal force, I can find the coefficient. So this is about forces. Let's identify the forces acting on the box. That's what a free body diagram is about, right? So I'll hit the easy one. I get to pick the first one. That's going to be weight. So let me tell me another force acting on the box. What's that? Normal force. How do I draw the normal force acting on the box? All right, easy enough. I think, using my common sense, that the normal force will be drawn equal to the weight. I don't see anything else acting up or down on the box. So this seems not unreasonable. Are there any other forces acting on the box? Yeah, I think friction. We're being asked about friction. That seems pretty likely, don't you think? Should I draw that to the left or to the right? I think we would draw it to the left. It opposes motion. The box is moving to the right, then friction should be opposing motion. Friction has to be to the left. Is there any cable attached to the box? Anybody pushing on the box? This is it. These are the only forces acting on the box. We've exhausted our list. So, what do we think? First law problem or a second law problem?
Second.
I think it's got to be second law. These look unbalanced to me. Sometimes it's easier to, but they clearly look unbalanced to me. So I'm going to say this is a second law problem. I have to choose a coordinate system that best supports this. How do you want me to draw this? What direction is the box accelerating? Left, right, up, or down?
Left.
Has to be accelerating to the left. The unbalance is to the left. The acceleration has to be to the left. The box is moving to the right, but the acceleration is to the left. Now, you have to make a choice here. And we've talked about these kinds of choices in the past. Choosing positive and negative is arbitrary. I'm definitely going to line up the x direction horizontally. Do you want the positive x direction to be to the left, or do you want the positive x direction to be to the right?
To the right.
Now, this choice doesn't affect your answer as long as you're consistent. Let me tell you what the differences are. If I make to the right positive, that's fine. Then when I make my net force in the x direction equals ma, I need, and you need to understand that friction is in the negative direction. I have to make sure we all say that. Everybody understand? But, hear me out. If I make to the right negative and the left is positive, then later on, I need to make this negative, and I need to make this negative. I need to be consistent. Does everybody understand? Now, this negative sign, you don't have to do this. It'll work itself out in the problem, but being consistent is important. So I would just encourage you to be consistent. That's all I would encourage you to do. So if it were me, I would make to the left positive. I think you'll be happier. Because we don't actually know friction very well. We don't know the answer to friction. So making an unknown the direction of positive tends to help. Not always. These are going to get more complicated, and you'll have to be more careful. But I'm going to do it this way. Ready? We keep going? All right. We're just about done. There's not a whole lot more we can do here. Net force in the y direction equals 0. So normal equals 50 newtons. That one's easy. Right? Normal equals the weight's 50. Friction equals m5 times a, but that's all we've got. So we're kind of stuck unless we can figure out what a is. Is there any information that's been presented that we could use to figure out what a is? Sure, yeah. This is the opposite of the last problem, right? In the last problem, we didn't have enough kinematics information and we used the forces to figure it out. In this problem, we don't have enough information about the forces. We can use the kinematics to figure it out. That's how this problem is different than the other problem. I have information. I have the initial velocity, -8 meters per second, and the final velocity, +8 meters per second. I'm sorry, +6 meters per second. I mean, -6. I can't even talk now. -6 meters per second. I know the displacement, the size of the patch was 3 meters. I could definitely find the acceleration. I have kinematics information. We've done these problems before. We're experts at them. Well, some of us are. Some of us were after the makeup test. Some of us aren't still. So v squared minus v naught squared equals 2a delta x. This one's on the equation sheet. There are 3 motion equations on the equation sheet. This is one of the ones that's on the equation sheet. That looks to be negative 6 squared minus negative 8 squared equals 6a, since delta x is 3. All good so far? Delta x is actually negative 3. Sorry, right? Because it travels to the right. So probably should write this as negative 6a. 6 squared is 36, minus 8 squared is 64, equals negative 6a. I don't know, you guys have calculators. 36 minus 64 divided by negative 6. I don't know what it is. 4.7. Sounds good to me. We good? Now, we're not done. Lots of steps, right? This, we're good at, right? Past that unit, we can do this stuff. So when we have kinematics information, it could be used to give us accelerations. We need to be aware of that. Come back over here. I now know the frictional force. It's 5 times 4.7. Which, I don't know, just a little bit less than 25, but I don't know how much less. 23.5? So it seems to me I have the frictional force and I have the normal force. Is that sufficient to find mu? Believe so. Coefficient of friction. 23.5 divided by 50. I think that's 0.65. No. 0.47. Mr. Shelton. Mr. Shelton had a near-death experience this morning. He's still feeling it. But let me tell you again, I have an elevator that has a person in it, and the elevator and the person together are 500 kilograms. There's a cable connected to the elevator that's pulling upwards on the elevator. I hope there's no doubt that this cable pulls upwards on the elevator. And the elevator needs to accelerate upwards at 2 meters per second squared. I want to know the tension in the cable. So I think we would just draw the forces in on this one. This one's pretty easy, I hope. How many of you agree that there's going to be downward force of weight? That seem good? And weight's equal to mg, or 5,000 newtons. That all good? Tension upwards. Now, to answer Hannah's question, I would probably make the positive y direction upwards. But that will mean that the net force in the x direction will be 0. Whatever direction you make the direction of the acceleration, the other one should be 0.